Okay, so last class I teach the final exercise, and as you can see, the condition is more complicated. This is we consider the curvature shape, and you need to apply the hydrostatic equation to understand how large the force requires acting on the curvature surface. So this exercise a little bit complicated due to we have the curvature size, and then you need to consider the different force directions along the horizontal and the vertical. So, but most of the step we follow first is we need to find out the hydrostatic force, the first. And the second, we need to understand where is the location of the hydrostatic force. And then the final, we always do the moment balance for our questions to figure out the final force we have. Okay, so this is a very famous exercise, and the next final exercise associated with the hydrostatic force are showing here. So as you can see, that's the questions we also need to find out the force required to open the gate. So the purpose for this exercise, we still need to find out the force required to open the gate. Okay, but as you can see, the final answer shown on the buttons. We wondering to provide the general formulas for the force is required to open the gate. Okay, so as you can see, I provided the final answers, but the gamma is the liquid specific weight, and the W is and the L is the dimension of the plate. Okay, so the W is the width and the L is the length of the plate. So we start from consider the flat panel first. And the second question is we change the shape to the curvature panels. So the first question is here, what is the magnitude of the reaction force acting at the point A? And you don't need to provide the certain answers. You need to provide the answer based on the gamma and the dimensions of the L and the W. So the L, again, is the length of the panels, and the W is the width of the panels. So, as I mentioned on the previous slide, for the first we need to find out the magnitude, how large it is, right? So, but the first, the step one, we should find out the hydrostatic force, right? So, for the hydrostatic force, we need to compute the hydrostatic pressure first. And we know that the hydrostatic pressure is equal to the gamma, right? The gamma is the liquid specific weight. And where is the center? Where is the centers of the gravity? Okay, so we need to know the Y bar. So we go back to see the figure here. We may point out there is the centroid point. There is the centroid point, and we have the length in here. We have the length in here, and the total length of the panel is the L. So actually, we know that there is the 2 over L, right? And we have the angle. We have the angle 45 degrees here. So we know that the length in here is 2 over L, but there is also the 35 degree in here. So you have the sine 35 degree in here. So the length along the vertical line in here is 2 over L sine 45 degrees. Okay, and before we deal the problems, we know that where is our crossover point at the surface, liquid surface. So this point we call that the O. So where is the Y bar? So we need to change the label here. We need to multiply the D bar, right? Because it's the vertical depth at the central point, the vertical depth of the central point. So the first we know that the D bar will equal to the, as you can see there is 4 over L. So the D bar in here, the total length we want to calculate is along here. This is our D bar. It's a central depth. It's a central depth. Okay. So we need to calculate the D bar first. So D bar is equal to the 4 over L and multiply the 2 over L and multiply the sine 45 degree. Okay. So the first we should compute how the centroid depth for the how large the centroid depth. So you don't need because we don't know how the length of the panels, so we just compute the answers we keep the L parameters and compute the other answers. So the sine 45 degree divided the 2 and plus the 1 divided the 4. So this is equal to the 0.6 and around the 0.36. Okay, this is our centroid depth, and we have the centroid depth, so we can compute how large the hydrostatic pressure we have. So the hydrostatic pressures in here is equal to the gamma multiply the 0.6036 L. Okay, and the second, how we need to compute the hydrostatic pressure, because we would like to compute the hydrostatic pressure force. And we know that the hydrostatic pressure force is equal to the pressures multiply the panel area. The pressure multiply the panel area. So we know that the panel area already shown here is L multiply the W width. Okay, so here you just keep the gamma. Maybe I put the number on the front. So 0.6036 and the gamma L. This is the hydrostatic pressure, and the multiply the area is the L multiply the W. So you know the hydrostatic pressure force is equal to 0.6036 and the gamma WL squared. Okay, so we have the hydrostatic force already. And the second, we need to find out where is the location of the hydrostatic force, right? So as we remember, we have the YCP minus the Y bar will equal to the second moment of the panel area divided the total area and the Y bar. So where is the YCP? The YCP is the location of the hydrostatic force. So we need to pick up the YCP maybe here. We have the CP point. So where is the YCP? The YCP is start from the CP along this direction to the O point. So the red line is the YCP length. The red line here is the YCP length. But we don't need to compute the YCP certainly, because we only need to know how difference between the YCP and the Y bar. So based on these equations, we first compute the Y bar first, because the Y bar is required to these equations. And we know that where is the Y bar? The Y bar is the point here go to the O point. Okay? So you need to compute the length for the blue line here. Okay? So as we know that we first need to compute the length in here. Okay? So we only know the Y length in here is 4 over L, right? So the length in here is 4 over L root of the 2. Because the angle in here is 45 degrees also. So we know that the inclined length is equal to the 4 over L multiply the root of the 2. Okay? So we know that what is the Y bar? The Y bar is the length is 2 over L. The 2 over L is here. Here is 2 over L. And the length in here is 2 over L multiply the root 2. Okay? So the 2 over L plus the 4 over L root 2. Okay? So you can compute how large the Y bar we have. So we use the calculator, the root 2 divided the 4 and the plus the 1, 2 over 1 is plus 0.5. Okay? So the length here, I compute the double check. The root 2 divided the 4 and the plus 0.5. So the length here is 0.8536 and L. Okay, so we have the Y bar. So the seconds, we didn't know how large the second moment of the I. And as we know in here, this is a right angular panel gauge. Okay, it's a right angular panel gauge. So we know that this is I will equal to, the second moment will equal to the 12. And right now, the rotating axis is along the, is into the paper. So the rotation axis, the length is W. So as I mentioned, for the rotation axis, the length is parallel to the rotating axis. The power in here is the 1. But the length of the panel here, is the L, right? So there is L is equal to the L cubic power. So I would like to emphasize how can we determine the 1 power or 3 power. If the length is the parallel to the rotating axis, the power you should keep the 1. And the length is perpendicular to the rotating axis, the power is the 3. So right now the rotating axis is the crossover to the point B and into the papers. So the rotating axis is parallel to the width. So that's why I use the 1 power in here. Okay? So you can compute the number answers. So there is the 1 divided the 12, and you have 0.0833 and the WL cubic. Okay? So since all the unknown parameter we already have, so we can first compute the YCP minus the Y bar will equal to the I right now is 0.0833 and the WL cubic. Okay? And divided the area, total area is WL, right? And also divided the Y bar length The Y bar length right now is 0.8536 L over 1. Okay, so you can cancel out some parameter you have. The width can cancel out, and we have the L square. So right now we only have the L1 powers. Okay, and then we put all the answers, the numbers. I check from my calculator. So the distance between the YCP and Y bar will equal to 0.0976, and we only have the L length. Okay, so we have the YCP minus the Y bar distance difference. Okay, so the third step, we should have the moment balance. Okay, we should have the moment balance. So I would like to replot. This is our the plane panel, and the point here is the B. Okay, and the red dot there is the CP point. So and we know that we have the force in here is the FP, right? It's a hydrostatic pressures, and right now the answer we need to require is the reaction force. The reaction force I use the RA is the reaction force acting on the point A here, and if we would like to compute the moment balance, so we need to project the force along these directions, and we know that the angle here is 45 degrees. Okay, so that means the angle here also the 45 degrees. So we can project the reaction force along the blue line directions. So the force in here is the R reaction force. Maybe use the cosine 45 degrees. Okay, reaction force project into the blue line directions. So the RA will multiply the cosine 45 degrees. Okay, and then we know that the momentum balance is the moment balance is FP multiply the distance between the CPB, right? The FP multiply the CPB distance will equal to the RA cosine 45 degrees and multiply the AB length. Okay, so that based on the moment balance between the positive moment and the negative moment. So the answer we need to require answer to how large the RA values. So the FP, we put the FP into the equation. The FP is here. We have the FP is here. So the FP is equal to 0.6036 gamma WL squared. And what is CPB length? We know that the point here is the centroid point, and this is the length in here is 2 over L, right? It's 2 over L because the total length is L, and we know that the YCP minus the Y bar here, okay, is equal to the 0.0976 L, right? So the CPB length is equal to the 0.0976 L plus the 2 over L is 0.5 L. Okay, will equal to the RA cosine 45 degrees, and the AB length in here is the L. The AB length in here is the L. So only one unknown parameter is the RA. Okay, only one unknown parameter is the RA. So you can put all of the number inside the equation and compute how large the RA we have. So for me, I can check the answers 0.0976 plus 0.5 and multiply the 0.6036. Okay, so the left hand side, the number is 0.361 gamma W and the L qubit, and will equal to the RA and the cosine 45-degree L. So it's equal to the 0.7071 and the L. So you can compute the RA. You can compute the RA will equal to the 0.631 divided 0.7071. So the final answer is around the 0.51, and we only have the gamma WL square. Okay, so it's similar, almost the same answers I already show on the buttons. Okay, so because for this question we don't put the certain number into the questions, because we would like to derive the final general equations for the plate panel. Okay, so in that case, if we know that this equation is specific for the angle for the 45 degree. So in the future, you put any plane gate with a different size. You can only follow this equation to compute the reaction force, how large it is required to open the gate. Okay, but if you change the angle to different, from the 45 degree to different angle, you need to derive the different final formula for the flat panel shape. Okay, so and I would like to emphasize the step for analyze. The step 1, you should find out the hydrostatic force first. And the second, you should find out the locations for the hydrostatic force. And the third one, you should apply the moment balance, and you can compute how large the force required to open the gate. Okay, so only the 3 steps you can finish the to try to find out the answer for the questions. So let's we move to the second, the B. The B questions is if we change the flat panel to the curvature panels, and then the RA is a reaction force at the A point will be greater than or less than or the same as for the plane gate. So for these questions, I don't recalculate the answers, even though I know right now I changed the curvature shape, but I don't need to compute the answer again, because as I always mentioned, you should consider how many fluid weight above your curvature. Okay, so but for this here, maybe this is the fluid weight I need to overcount. But the top, the case in here, the fluid weight I need to overcome is the blue regions, and the bottom is the yellow regions. So you just compare how different they are for the fluid weight. So for me, I understand the bottom one, the case in here, the fluid weight beneath the curvature gate is smaller than the top one. So that means the reaction force required to open the gate should be the less than the top case. Okay? So for me, I will say that the answer is less than. For the bottom case, because the fluid weight above the curvatures is smaller than the top one. The top here, the blue regions are quite larger than the yellow regions showing here. Okay, so for the second questions, we don't need to calculate the answer again because we can only figure out how many fluid weight for the gate you need to overcome. So for the top one, the fluid weight is larger. That's why we require the larger reaction force to open the gate. Okay, so this is a final exercise for our hydrostatic ideas. And in the future, if you have some hydrostatic example, and then you can apply the equation showing here. Okay, so we move to the next. So in our class, if we will some material associated with the laboratory experiments in the next semester, I will highlight on the PPT. So this is one of the laboratory experiments in next semester you will attend the class. So this experiment, we call that the hydrostatic experiment. And the figure showing here is our device. Okay, so in the next semester, you will see this device in our laboratory class. And all the laboratory experiments, I will tell you how many times is required to finish the experiment. So for this one, we should spend 30 minutes to finish the experiment. Okay, so we can go more details. So this is corresponding to the hydrostatic ideas. So as you can see, we have the y length. The y length in here is the water depth. So we can put the water into the device. And we can change the water depth here. The water depth is y. And we know that the certain distance is d. So in the first case, we only consider the water depth y is less than the water depth y is less than the d length. It's less than the d length. So we can, in that case, we can deal this problem with the flat. That's similar to the flat panel, right? For the flat panel conditions, that is similar to this one. So we know that we have the YCP and we have the FP, and we know that the location maybe here is the YCP. So we can compute the theoretical moment in this experiment. So but for the next semester, sometimes we always forgot everything. When I teach in the class, you may remember something equation you have. But in the next semester, for all students, maybe mostly forgot everything on the class we learned. So in our laboratory experiment class, I will provide two equations for you. So you just follow the two equations showing here. You know that how large the FP, right? And there is the YCP equation. So you can compute the theoretical moment based on these equations. Okay, you have the F, you have the A in here, you have the D in here, and you know that the YCP, how large it is. So follow this equation, you can compute the theoretical moment. Okay, and what is the true? So there is the true moment we have. And you see the true moment is equal to the M is the mass, and the gravity, and multiply the length, L. So where is the n? The n is here. So we know that the mass acting on here, and we know that the length, the capital length we have, and this is our the point O. So how can we have the mass in here? So as you can see, there is the recorder. Okay, so during the experiment, you will see how large the mass, and the mass weight will show on the recorder. So you actually know how large it is in here. Okay, so that experiment just try to compare the theoretical moment and with the true moment, and you will see how different they are. Okay, so the second conditions, the YCP, the Y water depth will larger than the D. The Y water depth will larger than D. So right now we consider the curvatures panel size. So this condition is similar to the curved panel, not the flat. So it's the curved panels. Okay, so based on the curved panel, we have the different YCP definitions here. So you can compute the different YCP location. And also follow the two equations showing here. You make the comparison between the theoretical moment and the true moment and compare each other. So I put the during the experiment, you should finish the table as I showing here. So you will compute the theoretical moment, and you have the true moment, theoretical moment and the true moment, and you will compute how the difference between the true moment and the theoretical moment. Okay, so sometimes and you have under the two different conditions, y is less than d, or the y depth is larger than d. Okay, so for our experiment, you just finish the table, and you should discuss why the reason there are a large difference between the true moment and the theoretical moment. Okay, so if you forgot the next semester, you may forget something equations, but in our experiment, I will provide all the equation, so you don't need to remember everything. You just follow the equation I show on the document, and you can finish the table. Okay. So we would like to move to the next topic. Okay. The next topic is corresponding to the buoyant force. Okay. And the buoyant force is applied to different purpose and different problems. As I just show some case for the design of ships or the sediment transport in the river, and also the fish migration will apply some idea based on the buoyant force. So as you can see, how can we define the buoyant force? So you have you pick out the one fluid particle. Okay, based on the hydrostatic condition, we know that the particle will static at these locations. Okay, so right now we consider different curvature line. The first one we consider ADC, the ADC curvature lines, and we know that the pressures, as I showing here, the pressures acting on the lower portions of the body. Where is the lower portion of the body? As I mentioned, the ADC line. Okay, and we will have the upward force. The upward force to support will equal to the weight of a liquid need to fill the volumes above the surface ADC. Okay, so that means we have the force up, and this force up should be support the fluid weight above the ADC curve. So the fluid weight is the gamma, and what is the volumes we have above the ADC. We have the volume the A plus the VB, right? We have the volume VB here and have the volume VA here. So because the particle stated here, so the ADC curvature lines will have the upward force to support the fluid weight, to support overcome the fluid weight above the ADC line. Okay, and the second we consider the different curvature is the ABC. Different curvature is the ABC. And you can see the sentence shown on the right. The pressure acting on the top of the surface body ABC create the downward force equal to the weight of the liquid above the ABC. So that means we have additional force is the downward. So we have the F down. And the F down is caused by the fluid weight contributed from the volumes of the VA. So we have the gamma VA. We have the gamma VA, right? So for these questions, we need to require additional force to balance all the force we have. And then the particle will static here, okay? So that we can compute the force balance. So the F net will equal to the force up minus the force down, right? And we know that the force up is the gamma VA plus the VB, and the force down is the gamma VA. So finally, we only have the gamma VB, right? So the final net force is equal to the gamma VB, okay? And then we call that is the buoyant force. So finally, we call that this is the buoyant force, and we use the FB. So what is the buoyant force? The buoyant force is related to the liquid specific weight, gamma, and also associated with the displaced volumes. Okay, what is the displaced volume of the body? The displaced volume of the body is the VB. Okay, so there is the displaced volumes of the body. Okay, so that means the buoyant force is equal to the gamma and multiply the displaced volumes of the body. Okay, so that is Archimedes principle, right? Because we know that even though the body is floating, as you can see on the figure, the body is floating, but we only need to consider the displaced volumes we have, and then we can compute the buoyant force, okay? And then we can compute the buoyant force. So you can see the buoyant force is equal to the weight of the displaced fluid. The weight of the displaced fluid. And just based on this idea, Archimedes principle, we can develop the hydrometers. Because the hydrometers, we can put the hydrometer inside the liquid. And because the liquid, if the liquid change the specific gravity, Sg, and then we will have a different buoyant force, right? And the different buoyant force, we have a different specific gravity scale. So that we can apply the Archimedes principle to design the hydrometers. And the hydrometer will, you put the hydrometer into the liquid and you can read the scale to understand how large the Sg for the liquid. Okay, so that's just the applications for the hydrometers. Okay, so but the most important thing is the buoyant force. The FB is always equal to the liquid gamma and multiply the displaced volumes of the body, of displaced volumes of the body. Okay, So we can try to do some exercise and will be better understand how the buoyant force we have. Okay, so for these questions, we have the two targets. The first target is here. The first target we know that is the floating wood. Okay, this is the first target. And the second target is the metal part. Okay, in here, we have the metal part in here. And how the liquid we have, the liquid right now is the water. So we just put the wood and the metal inside the waters. And this is the figure show the final balance we have. Okay, so we just draw some bodies diagrams we have. So the first we will have the weight. The weight is going down, right? This is the weight. It's caused by the wood, the floating wood. And we should have the FB, right? We will have the buoyant force is the upward force. Okay, and then this is a cable line, and the cable line will downward tension force, and we have the opposite tension force for the object 2, right? And the object 2, we also have the downward weight, and we also have the upward buoyant force. So because we have the two objects, so maybe here I use the W1 and the FB1, and here is the W2, and there is the FB2. Okay, so based on the force balance, you should compute how large the tension force you have. The tension force we didn't know is the T, and we didn't know the mass of the metal. So here we can rewrite W2 is equal to the N2G, right? And because we need to answer the N2, how large it is, and we need to answer how large the tension force T in the code. Okay, so I just write down all the force diagrams. And so the first, for the object 1, we can only focus the object 1. Okay, the object 1 we need to have the balance is the only one upward force is the FB1, and the two downward force is W1, and the plus the T. Okay, and the plus the T. And we first consider we need to compute the FB1, right? And the FB1 is the gamma. Gamma right now is the water, so we have the gamma water and multiply the displaced volumes. Okay, the multiply the displaced volume. So what is the displaced volume for the floating width? Okay, so you should cut off the water surface line in here, and the displaced volume is the yellow regions. Okay, the displaced volume is the yellow region. So we need to compute the displaced volume first, and then we will have the buoyant force. Okay, so based on the figure, we know that the displaced volumes. The first we know that the size. The size is 50 millimeter width and 50 millimeter length, and the depth is 10 millimeters. Okay, so we know that the 50 millimeter length and the 50 millimeter width, but right now the depth is the 10 minus 2.5, right? Because we need to minus the 2.5 millimeter because it's above the surface liquid. Okay, so we can compute the displaced volume is equal to the 10 minus 2.5 and multiply the 50 twice times. Okay, So that will equal to the 1.8750 millimeter cubic. And we can convert it to the meter square, meter cubic. So that will equal to 1.875 10 minus 5 powers meter cubic. Okay, so we can recalculate how large the buoyant force we have. So the gamma W is equal to a 9A10 and Newton per meter cubic, and multiply the displaced volume is 1.875 10 minus 5 meter cubic. Okay, so you can compute your buoyant force in here is equal to a 0.18 maybe 39 Newton. Okay, so we have the buoyant force, and the second we can compute the weight of the floating wood. So we should have the gamma wood. So we should have the gamma wood, right? And multiply the total volumes of the wood. The wood of the total volume is the 50 multiply 50 and the 10 millimeter. Okay, and then we need to multiply the 10 minus 9 power to convert the millimeter cubic to the meter cubic. Okay, so what is the gamma wood? The gamma wood, because we have the specific gravity is 0.3. Specific gravity is 0.3. So here is the gamma W multiply 0.3 Sg values, and the following volumes I compute by the calculator. So it's equal to the 2.5 10 minus 5 meter cubic. Okay, so we put all the number inside the equation and calculate the answer. Okay, so I check the answers. That's the weight from the wood is 0.0735 Newton. Okay, so you have the FB values, buoyant force, and the W weight, and then you can compute how large the tension force we have. So the tension force will equal to the FB1 minus the W1, right? Okay, so all the number answer you have, so you can check from your side. So I check from, based on my calculator, is 0.110 Newton around. Okay, so we can answer just based on the object one and the force diagram balance, and we can compute how large the tension force we have. Okay, and then we can move to the second questions. Again, for the object 2, and we also can write down the force balance. So again, we have the FB2 is the upward force will equal to plus the second upward force is the tension force will equal to the weight of the metal. Okay, so we already have the tension force, so we need to compute how large the buoyant force for the metal. So again, we know that the FB2 will equal to the gamma W multiply the displaced volumes of the body. And right now the displaced volumes, we have the total volumes immersed into the water. So we just apply the total volumes of the metal as the question show. the total volumes numbers. So we know that the 9A10 Newton meter cubic multiply the total volumes of the metal is 6,600, and we know that we need to apply the 10 minus 9 power to convert the unit to the meter cubic. Okay, so we can compute how large the buoyant force caused by applied to the metal. So the 9A10 multiply the 6,600 and multiply the 10 minus 9 power. So that's equal to 0.0647 Newton. Okay, so we can compute the W2. The W2 is equal to the FB right now is 0.0647 Newton plus the tension force. The tension force we know that is 0.11 Newton. So the weight is finally equal to the 0.1748 Newton. Okay, so but the questions we need to answer is the mass. So we know that the mass will equal to the W weight divided the gravity. So you can divide the answer weight by the 0.81 gravity. So we have the 0.0178 kilograms. And then you can convert the unit to the gram is 17.8 G. Okay. So this is a very simple questions. We just first we make the force diagrams, and based on the force diagram, you can have the force balance equations, and for each topic, each object, you can find out the answers based on different object force balance result. Okay, so this is we just only have one idea. So we just keep the idea is the buoyant force is equal to the gamma multiply the displaced volumes of the body. Okay, the gamma multiply the displaced volumes of the body. So that's the buoyant force. Okay, and then we have the second exercise, and maybe we can finish this exercise, and then we have the 5 minutes break. Okay, so this is exercise is a very common ideas because we have the hot air. Okay, we have the hot air balloon, and we actually know the volumes of the balloon is 2,000 meter cubic. It's 2,000 cubic meters. Okay, so I may write down some conditions. So we have the volume of the hot air. The hot air is inside the balloon. Okay, so we know that the V, maybe I use the VB, okay, is equal to the 2,000 cubic meter. Okay, and inside the balloon, the temperature here, the TB temperature here, we have the 100 degree, and the pressure inside the balloon is the 120 kilopascal. Okay, this is the inside the balloon, the condition for the pressure, temperature, and how large the volume we have. And we have some condition for the atmosphere. Okay, the atmosphere pressures, I may use the PA, is 101.3 kilopascal, and the temperature conditions for the ambient is 10 degree. Okay, so that's the problem is what is the maximum loading weight can be supported by the systems. That's sometimes we need to make sure how many people inside here can be supported by the buoyant force, right? If the buoyant force is not large enough, we cannot save all the people inside the balloon. So that's a very common idea. We need to design the different systems and to support the different peoples can go uplift to the sky. Okay, so that's what are the questions. So we should make the force balance. So how many force balance we have? So maybe this is our systems, and then we know there is some requirement. We should have the buoyant force, right? We should have the buoyant force. And there is the people. We have the people weight. We have the people weight. And we also have the weight. We also have the weight that contributed by the balloon, right? We also have the weight contributed by the balloon. So that's the force diagram. We have the buoyant force first. And the buoyant force need to overcome the people weight. The people weight is the W here. And need to also overcome the self weight. The self weight also the weight contributed by the balloon. So that's our force balance. So the first idea is we need to have the FB. So we should compute the FB, the buoyant force. As we know that the buoyant force is we need to have the gamma liquid, right? Right now the gamma liquid is atmosphere air. So we should have the gamma A. We should have the gamma A. And the gamma A need to multiply the displaced volumes. So right now the displaced volume is the VB, right? Because the displaced volume is the balloon. It's the balloon volume is the VB. So this is our buoyant force. And then what is the WB? The WB is the weight of the balloon. So we need to have the gamma balloon and then multiply the total volumes. Okay? And then the questions, we need to answer the W because we didn't know the W. The W is the people weight. Okay? It's the people weight. How many people can support by the balloon and the uplift to the sky? So we don't know this W, how large it is. So, and then because the questions, there is no gamma values. We don't know the gamma, how large the gamma A and how large the gamma B. So if you remember, the gamma is equal to the rho AG, right? It's the air density multiplied the gravity and multiply the total volumes displaced on the air. And the gamma A again is the low, gamma B is the low B, G, and the total volumes, right? So that's the key knowledge. We didn't know the density for the air and the balloon air. Okay? So that's the idea. We can start from the ideal gas law. If you remember the ideal gas law, the IGL tells us the relationship between the pressure will equal to the rho RT, right? The pressure will equal to the rho RT. So we know that the rho will equal to the pressure divided the gas constant and the absolute temperature. The absolute temperature. So now we can convert the absolute temperature. This will be the T is 373 Kelvin, right? And here we can convert the absolute temperature is equal to 283 Kelvin, right? So So we can individually compute the density for the air and then the balloon air. Okay, so I wondering to compute the density first. So the density A is the atmosphere air will equal to the atmosphere pressure PA divided the R and absolute temperature TA. Okay, and we know that the PA is the 101.3 powered par divided the gas constants I already support here. So you can write down the gas constant is 2A7 Joule divided the kilogram and the Kelvin. And the temperature in atmosphere is 2A3 Kelvin. And you can compute the final density for the atmosphere air. Okay, so I check by my calculator, the number should be equal to the 1.247, and the unit is a kilogram per meter cubic, right? And again, we can follow the similar ideas to compute the balloon air density. So the PB pressure divided the gas constant multiply the absolute temperature for the balloon. So right now the pressure is 120.10.3 power par, and again divided the same gas constants, the Joule, kilogram, Kelvin, and the absolute temperature right now is 373 Kelvin. Okay, and you can compute based on this. I check the number again, and should be a little bit smaller than the air. Okay, so this is 1.12 around the 1 kilogram per meter cubic. Okay, so we have two density properties, and then we go back to see our questions. So based on the three equations showing here, I make the force balance. The FB should be supported the weight B, the balloon, and the plus the W. Then the W will equal to the FB minus the WB, right? FB minus the WB. And we know that the FB is the gamma G, rho AG VB in here, and this rho BG VB in here. Okay, so we know that the G and the VB are the same. So the inside is rho A minus rho B. Inside is rho A minus rho B. And the questions we require to answer the loading weight, and the final answer is the M. So we know that the W can be rewritten by the mg. Okay, the W can be rewritten by the mg, and will equal to the GVB multiplier density difference. So we cancel out the G both sides. So the mass is equal to the VB multiply the density change. Okay, so we just put the number inside the equation. So the VB here, is 2,000, right? Meter cubic, and the density difference is 1.247 minus the 1.121. And the unit is a kilogram meter cubic. Okay, so you can double check the answer by your side. And for me, it's around the 252 kilogram. Okay, So maybe the one people around the 40 to 70 kg. So you can consider how many people you can support on the balloon. So it's under this systems. And in other words, the most important key knowledge is the density difference. So if you can design the systems with the larger density difference, you can support the more peoples. Okay, so that means you don't need to always use the air to support the buoyant force. You can also use the different gas and will have a different supporting force. Okay, so that's I guess this is a very good exercise in our common life. Okay, so but I would like to emphasize only one ideas for the buoyant force is you have the gamma liquid. So you need to know how kind of the liquid in your systems. And you need to consider your displaced volumes of the body. So you don't need to consider all the volumes of the body. You only need to consider displaced volume of the body. And then you can compute the buoyant force. Okay, so that is a final exercise for the buoyant force. And after our 5 minutes break, we will go back to teach the stability problems for our bodies. And we actually know the two different conditions. Is we only consider the immersed and the floating bodies. So two conditions we will try to teaching some ideas, and we have the exercise to practice. Okay, so may we have the 5 minutes break, and then we'll go back to class and finish this chapter.